All right, welcome to Unit 5, Day 1, Derivative of Sines and Cosines. So we're going to actually discover what the derivative of these trig functions is instead of just me telling you, just like we discovered what the derivative of the exponential functions were in the last unit. So we're going to do it by going to Desmos. So in the link, you're going to find a spot to go to Desmos, and this activity is going to pop up. I'm just going to do the first few demonstrations, and then you can do the rest of this activity on your own. So what you'll see here is a sine curve, and what we're going to investigate is what the derivative of sine is. And we're going to do it graphically. So I have this, and I've got the slider here that is measuring the slopes of all different sorts of tangents at different points. And so you're going to take the derivative of all these points, or the slopes of all these tangents, to come up with the derivative. So we're going to do it like we've done in the past by doing the stuff down here. So you're going to start off with going to 0. So put your slider at 0. We'll write down the y coordinate at 0. So just the regular sine function. Of course, sine of 0 is 0. And then we're going to record what the slope of the tangent is. So if you look here, we have to see, and apparently the slope of the tangent is 1. Okay. So and then when you're going to move over here, oops, just going to move this one notch to the right, and you see that this slider goes up by pi over 4 intervals. So it doesn't look like pi over 4, but this is actually the sine of pi over 4. So the sine of pi over 4 apparently is 0.707. So you can put that in. The 3 decimal places is fine. And it turns out, interesting, that the slope of the tangent at that spot is also 0.707. And then you can move on and do the next one. Do the sine of, this would be pi over 2, okay? And then go and do the slope and the y-intercept. And plot these purple points. And when you do that, then I think what you'll discover is an interesting shape that is the derivative of sine x. So I invite you to pause the video now and go back to Desmos and put in the code and try that activity and see what you discover. Okay, so we're back here, and hopefully you discovered some pretty cool derivatives of sines and cosines, and also went a few steps further and kind of discovered the entire lesson here and how you're going to actually differentiate sine and cos. But I've got a couple of further examples, like more traditional examples that you can follow, but you will see the same sort of questions that you did and discovered in the Desmos activity outlined in this activity here. All right, so here's the discovery that, of course, the derivative of sine is cosine. Okay, that each of the slopes of the tangent ends up following the exact same pattern as cosine, which is actually pretty remarkable. And then you discovered that the derivative of cosine is negative sine x, that it looks an awful lot like a sine, but it's just a negative version of it. Okay, all right, so the big conclusions then, and if y equals sine x, the derivative of sine x is cos x. And if y equals cos x, the derivative of cos x is negative sine x. In this video, we're just going to be investigating the derivatives of cos and sine, and then we'll look at the derivative of other functions on our next day. So here's a couple of examples. Of course, we're now going to differentiate stuff a little bit more interesting than just sine x. So we're going to differentiate y equals sine 3x. So hopefully in the video, or sorry, in the Desmos activity, you discovered, of course, that sine x is like an outside function and 3x is like an inside function. And so when you're taking the derivative of sine x, you first the derivative of a sine, and so the derivative of a sine is cos, and of course the 3x is there. Then you go inside and differentiate the inside function, that Russian doll idea, and the derivative of just 3x is 3. And then we can, just for appearance sake, take this and put it out front so there's no confusion as to whether it's part of the cos. It's just times 3, and so we end up with this. And therefore the derivative of sine 3x is 3 cos 3x. And I think that the one in the video you did was sine 2x, but you discovered that one was, of course, 2 cos 2x. All right, doesn't matter what you're taking the sine of, that inside function, because you're still going to do the same idea. The derivative of the outside is cos, so cos of whatever's there, so cos of x cubed, leave the x cubed alone first, then go inside and differentiate the inside, and the derivative, of course, of x cubed is 3x squared. We'll move that out front, and then you get this 3x squared cos x cubed as the derivative of this function. So it behaves just like the e to the x functions, the ln functions, cubic functions, and polynomial functions. All the same rules work when differentiating these trig functions. Okay, let's look at a couple of more. Of course, those ones were sine. If I'm differentiating cos, so of course the derivative of cos is negative sine, whatever's in there. You've probably heard me say like the derivative of cos blah is negative sine blah. You leave the blah alone, then differentiate inside, and the derivative of blah is 5, or the derivative of 5x is 5. So when you differentiate this, the derivative of cos whatever is negative sine whatever times the derivative of the inside. Of course, we'll move that out front and multiply by the -1, and we get negative 5 sine x. And again, we can up the ante by doing the derivative of cos of this polynomial, this little quadratic. So the derivative of that, of course, is sine of whatever. Okay, so inside that, you just leave as x squared plus 2. And then differentiate inside like its own little question is 2x, right? Of course, the derivative of 2 is 0, so that's gone. And now bring that 2x out front and multiply it by the -1, and the derivative of this then is negative 2x sine x squared plus 2. You've got the basics here, and now we can just include some newer functions, some other ones. So here's an interesting one. This is sine cubed of x. Remember that this notation actually means sine x times sine x times sine x. So it's written like this. You can imagine as this: sine x times sine x times sine x, or sine x cubed. The reason it's not written like that is so there's no confusion of like sine x cubed. You're not taking the sine of x cubed. It's the sine x, which is being cubed. So to avoid that confusion, our notation puts the cube there to just let you know you're doing the sine function 3 times. It just happens to be the sine of x. But for the point of differentiating, this is a little confusing. It makes more sense to write it like this. Now this becomes a outside function, inside function. The derivative of an outside function, the product rule or a chain rule happening, that's the derivative of a function rule, the product of a function rule. So the derivative of this then, okay, so it's between something cubed. So the derivative of something cubed is 3 to whatever that is squared. And of course that inside thing just stays the same. Outside in, Russian doll, first to the outside part. Now differentiate sine x. So now you go inside times, what's the derivative of sine x? Well, it's just cos x. And then technically you actually even go even further and take the derivative of x, which is 1. But we rarely write that down. We know the derivative of the sine x is just cos x. Again, this can be tidied up by bringing that 3 and bringing it out front and multiplying with the 3. You might see it written like this. You might see it without the brackets. You might have the sine squared first. Most often you'll see it like this without the brackets, but of course it's not wrong this way. And there's no rule that says the sine has to go first, although some textbooks do like that. Okay, so now we could take a bunch of that and combine all those rules. So this is sine cubed of x squared minus 1. That means sine of this times sine of it times sine of it. So it's the whole thing being cubed. So again, really think of the Russian doll idea. We're taking a big thing and cubing. So when we differentiate it, it's 3 times something squared. Okay, that's the outside function. The inside function we leave alone. Now we look at this inside function. It's like its own little question. So you differentiate this. So this is the sine of something. So again, your times, what's the sine of the derivative of sine? It's cos of whatever that thing is. That stays the same. Then differentiating even further, now you go inside and you've got this x squared minus 1. What's the derivative of that? 2x. Okay, and so we've done the outside Russian doll once, Russian doll twice, Russian doll 3 times to get it down to here. Tidy this up, we get a 2x times 3 and gets a 6x. This you can this you can bring out front here as well. And then this you can rewrite as a squared. So that squared can go back here. Just like we took the 3 out, we can put the 3 back in, or the 2 back in. Okay? Or of course, you might be happier if the sine x was here. Again, there's no particular pattern as to which way you write it. Okay? All right. Now, all the other rules, not just the power of a function rule or um, any of the other differentiation rules, the chain rule, the Russian doll idea, but all the other product rules and everything like that apply. So this one, I want you to be able to identify as one function being multiplied by another function. So the first function is x squared, and the second function is cos x, and they are being multiplied together. So that means, of course, we need the product rule. And the product rule tells us is the derivative of the first times the second plus the derivative of the second times the first. So let's do that all on the steps. The derivative of the first is 2x. What's the derivative of cos? Well, the derivative, oh, sorry. Let's backtrack. Let's start over here. All right, let's do that again. Sorry. There's the product rule. All right. The derivative of the first, okay, is just x squared times the second. Leave it as is, right? Derivative of the first times the second plus the derivative of the second. Okay, well, what's the derivative of cos? It's negative sine x times the first, and then times the first. Okay, so derivative of the first times the second plus the derivative of the second times the first. Okay, we can tidy this up, of course. This second part, a plus times or plus and a negative, of course, gets us negative. I'll bring that x squared out front, and we have 2x cos x minus x squared sine x as the derivative of this product rule. And the last example here is y equals tan x, and that I'm just going to let you think on. You could probably figure this out. I think actually I have confidence that you can figure this out, but this is where we're going to start in our next lesson when we take the derivative of tan. So everything we're going to do right now is only going to have questions with sine and cos. All right, for our final example, of course, here's our classic calculus question. I promised every time we introduce a new function, we would be asking this question. Find the equation of the tangent to the graph y equals x cos 2x at a certain point. Okay, so here's the function. We want to find the equation of the tangent, not just the slope of the tangent, the equation of the tangent at this spot. So of course, if we need to find the equation of the tangent, we need y equals mx plus b, so we need the slope. And of course, the slope is found by taking the derivative. So when you look at this, we again see a product rule. The first function is x, the second function is cos 2x. So it's the derivative of the first, the derivative of x is 1, times the second, which is just cos 2x, plus the derivative of the second. Well, the derivative of the second is, this is a cos, so the derivative of cos is negative sine. So negative sine, leave the 2x alone. Then differentiate the 2x. Okay, all of that is the derivative of the second. Don't forget that too. A lot of people forget that too. That's all the derivative of the second times the first. Okay, and another group of people forget that part. So again, derivative of the first times the second plus the derivative of the second times the first. Don't forget that first x. Okay, we tidy this up a bit. Of course, that's just 1 times 2x, cos 2x is that. This positive and negative could become a negative. Bring the 2x out front. We get negative 2x sine 2x. Okay, that's the derivative, which is the equation that describes all the possible tangents. We're only interested in the slope of the tangent at x equals pi over 2. All right, so which means wherever we see x, we're going to replace it with pi over 2. So there's an x that gets replaced to pi over 2, there's an x that gets replaced with pi over 2, and there's another x. Of course, all of these x's are being multiplied by 2. So it's 2 times pi over 2. Well, pi over 2 is a half of pi, and if you multiply it by 2, of course, you're just left with pi. And similarly, this negative 2 times pi over 2 is just negative pi, and 2 pi over 2 here is pi. And so we end up with cos pi minus pi sine pi. Okay, now this is a number because we've now substituted the value for x. It's not a variable, it's a number. But we actually can simplify this number even better. What is the cos of pi? Well, whenever I'm asked that, I always just imagine the cosine curve in my graph. And pi is halfway. Remember, the period is 2 pi, so pi is halfway. And the cos of it is negative 1. And then minus pi. Okay, but what's the sine of pi? Well, again, I just imagine the sine curve, and halfway is pi, and that's 0. So it'll be negative pi minus 0. Or sorry, negative pi times 0. Well, of course, since the sine of pi is 0, you multiply it by this, that whole thing is 0, and you're just left with the slope is negative 1. So it turns out the slope of the tangent at this spot for this function is negative 1. So we're halfway there. We've got the slope. We're going to plug that into y equals mx plus b, and we know it's negative 1x plus b. But what we need now is a point with x and y values to plug into this to solve the y-intercept, the b part. So where do we get their point? Of course, we go back to the original. The original question gives us an x value. We just need a coordinate for the y value. So how do we do that? Of course, we take it into the original. So we're going to replace this function and put that into the original function. So wherever you see x, you're going to put pi over 2. And wherever you see that x, you put it there, you get 2 pi over 2. Of course, that 2 pi over 2 reduces to 2 times pi over 2 reduces to just pi. So it's pi times cos pi. Of course, what's cos of pi? We just discovered that over here. The cos of pi is negative 1. Multiply that by pi over 2, and you get this negative pi over 2. So the coordinate where this tangent is an x value of pi over 2 and a y value of negative pi over 2. Now we have an x and y coordinate that we can sub into the equation to solve for b. So the negative pi over 2 is a y value, x is pi over 2, gets multiplied by negative 1. That negative 1 is going to, come across to the other side. So this is a negative pi over 2 becomes a plus pi over 2 when we add it to both sides. And then lo and behold, negative pi over 2 plus pi over 2 is just 0. So it turns out that with this y-intercept with this slope of negative 1 and this y-intercept, we actually have a very easy equation of the line. Y equals negative 1x plus 0. Now, this happened to work out really nice. Maybe you might end up with a pi over 2 that would be your y-intercept. Maybe you have a slope that's a little bit more complicated. But really, the point of this question is to practice your calculus here and then use it to find the equation of your tangent. So there's a quick rundown of the questions that we've done today. I'm going to invite you to do some practice on page 400, numbers 1 and 2. In there is mixed in some questions of tan. So save those. We're going to do the derivative of tan on our next day. So right now, you're just going to look in the questions on page 400, number 1 and 2. Pick a few to do. I'm not expecting you to practice them all, but there are definitely a couple that are worth trying. All right, and good luck with all of that.